Good morning. So I'm Abhradeep from UC Santa Cruz. This is a joint work with Adam Smith from Penn State and Jalaj Upadhyay from Penn State. Jalaj is the youngest author in our work, but unfortunately because of visa reasons he cannot be here, so I'm giving the talk. So this talk is about distributed private learning. So typically you can think of there are a bunch of devices. Each device has a data sample, and there is a server which wants to train a learning algorithm on these devices, and the trained outcome is a model. Now, in our work, what we show is protocols which are almost fully parallel in the sense, under the constraint of privacy, that server can talk to each of these devices independently and still come up with a reasonable model. Well, as you increase the complexity of the problem, meaning the number of parameters in the model or in the data, the degree of parallelism that you can achieve goes down. We also have some impossibility results which shows that if you are dealing with a sufficiently complicated problem where the number of parameters in your model is high, then you cannot avoid some degree of interaction, meaning that the server has to talk to a few of the devices, see the response, and then ask another question to a bunch of devices. Although this is expensive in implementation, but you cannot avoid for such kind of problems. So by now I've told you about what is distributed learning. We want to work with privacy. Let's kind of clear out these jargons. So the first thing I want to clear out is what is machine learning, and I will give a very stylized view. Suppose we want to train a classifier for Parkinson's disease. So from the phone, you can have some kind of a gyroscopic feedback from the phone or haptic feedback from the screen. And we want to train an algorithm which for a particular person would tell whether this person has a Parkinson's disease or not. Now, how do you typically do that? You will take a bunch of devices with such kind of information and train a learning algorithm which, let's say, would use the yellow dots to represent the people with Parkinson's disease and the blue dots the people who do not have Parkinson's disease. Now, like with a straw man picture, you can put this on this graph with blue points with negative examples and the yellow points with positive examples, and then you basically try to fit a model or a classifier which basically separates out the blue points from the yellow points. Now, these are the kind of problems we will be looking at here, and we want to solve them under the constraint of privacy. So that brings us to our next setup, distributed machine learning. So typically in standard machine learning, the data is lying on a server or a data center, and there is a learning algorithm which has direct access to all the data points and is training a model or a classifier. But now we are looking at this setup which is highly distributed, to the extent that every user has their own data samples with them. It may be on a phone, and there's a server like Apple or Google which wants to use this data sample to train a model. Now, the moment we move on to distributed setup, there are a lot of challenges that come up. First is the rounds of interaction that server has with the devices, and these are usually very, very expensive. And also, well, this is a privacy talk. Also, we are concerned about the implications of privacy in this setup of training distributed models. That brings us to privacy in distributed learning. So now, here, the data is distributed across devices, as I told you, and the device sends some information to the server, and the server uses this information to train or learn a model. Now, there may be an attacker who is actually observing the model to infer information about the device or the person holding the device. Furthermore, even more critical, the adversary may be actually the server who has access to the information that is being sent by the device to the server. So we want to protect against attackers of this nature, and as a result, we'll just assume the trust boundary to be the device itself. Anything that is coming out of the device should be considered untrusted. So the attacker should have access to everything that comes out of the device. Now, the notion of privacy we'll consider in this talk is what is called local differential privacy. A variant of this notion was initially proposed by Werner in 1976. Another variant was proposed by Efimetsky, Gurke, and Shrikant in 2003. And the final version, which I'm going to talk about, is by Dwork, McSherry, Nissim, and Smith from 2006. So here, you can think the device as a data sample. It runs an algorithm on this data sample and produces some information which is sent to the server. Now, for the purposes of the talk, consider this algorithm to be randomized. So A of D is actually a random variable. Now, consider a contrapositive scenario where I have changed this data sample to D prime, and the algorithm runs as it is on this data sample and produces the information and sends to the server. From the perspective of privacy, the requirement is that A of D, the random variable, and A of D prime, the other random variable, should be close in distribution, which in simple terms means that if I change your data sample, then the output of the algorithm does not change significantly, and as a result, it protects the privacy of the data sample. Now, there are very nice properties of this definition. First is that it is characterized by a single parameter called epsilon. It is not important how this parameter is related to the definition. Just remember that it's a privacy knob. Smaller the value, stronger privacy you get, and typically a small number like 0.1 or 1 is good. Furthermore, this definition is resilient to arbitrary auxiliary information. And the most important thing is that it protects against membership attacks provably. So these are the good parts of this definition. And we are not the first person to use this definition in the context of learning. There have been previous research which has tried to understand the relationship between this definition of differential privacy and how they scale with learning problems. Now, while trying to design these algorithms for learning problems, there is an apparent tension between utility and privacy. You want to be sufficiently accurate to give information. At the same time, you want to protect the privacy of the individual so that you are not overly accurate. And over the years, we have known that balancing this trade-off is hard. There have been series of attacks which basically forced the community to think about this problem from a more formal and concrete perspective, and hence we have resorted to a formal definition like differential privacy. Now, in this talk, I will use another leg in this picture, which is the interaction. So till now, people have been trying to understand the conflict between utility and privacy. What I'm going to convince you is that if you want to deploy such systems in practice, interaction is almost as important as the privacy utility trade-off. So what do I mean by interaction? We are in this distributed setup. The server is talking to these devices. Each of these rounds of communication to the device back and forth is actually expensive. And if you are, let's say, training your learning algorithm on number of iPhones, which is like around 300 million, then it is a lot of back and forth communication and slows down your system significantly. So what do we do in this work? We provide new protocols which are almost fully parallel. For certain class of problems, we can actually get completely parallel protocols, which means the device can talk to the server can talk to these devices independently and use that information to produce a model. So there is no dependency on the server to see the information from some devices and ask another question to other devices. But we also have some bad news. The news is that if you are looking at general learning problems where the dimensionality or the number of parameters in your problem is high, then it is not possible to get fully parallel protocols. So what is complete parallelism? Let's kind of delve a bit deeper into that. So each device interacts with the server independently and only once. So both these terms are important. You want to interact, the server wants to interact with the devices independently. So one interaction with one device should not be influenced by the interaction with the other device. At the same time, you want the server to interact with the device only once, because the device may not be up all the time. There are other issues with the devices, like they may not be on the Wi-Fi and things like that. So you do not want to rely on the availability of the device to design your algorithm. So how, at a very high level, how does this algorithm work? The server asks a bunch of questions, devices give the information back to the server completely independently, and the server produces a model. Now there are classes of problems where you can design such algorithms. slightly more different scenario is where there is completely adaptive interaction. So this was the state of the art before we started our research. So this was the work by Ducci, Jordan, and Wainwright from 2013, where they designed algorithms for machine learning problems exactly in this distributed setting, but their algorithms are completely adaptive in nature in the following sense. The server will talk to the devices in a sequence, and it would use the information that is received from one of the devices to ask the question to the next device. Pictorially, it asks, gets the information, asks the next device, gets the information, and this process continues. While this algorithm actually achieves the minimal error which is achievable under privacy, but if you try to implement these algorithms in practice, there's a huge bottleneck of the number of rounds of interaction you have with the system. And this is where we spent a lot of our time on to figure out how to design algorithms where you can minimize these rounds of interaction. So again, this work is about distributed private learning with local differential privacy. We design algorithms that have little or no adaptive interaction. We have some bad news where we show that we cannot get accurate general algorithms for reasonably high dimensional problems with no adaptivity. So adaptivity is somehow ingrained into the problem in itself. So talking about previous work, Kashi Vishwanathan et al. In 2008 actually introduced the problem of local private learning. The work of Ducci et al. In 2013 actually should be, they showed tight upper and lower bounds for this problem. So they actually gave algorithms which have minimal error. But the main caveat in their algorithm is that the number of interactions you have is exactly the number of devices you have. Now think if you have like 100 million plus devices, you really will have 100 million interactions to get to the minimal error, which in many scenarios is unacceptable. But one of the good features of their algorithm was that their algorithm still talked to each device only once. So differential privacy, or in fact local differential privacy, has gone some traction in recent years. The work by Google Rapport in 2014, they designed algorithms to figure out frequent websites people visit. Then I was also fortunate to be in the work which Apple basically introduced differential privacy in iOS 10, which is about figuring out frequent emojis or the new words that people are typing. But all this boiled down to computing simple frequency statistics. Now, when I was working at Apple, my knee-jerk reaction was to extend this work to more challenging problems like machine learning, but immediately I faced this impediment of the number of rounds of interaction. It turned out that algorithms which are existent at that time, they're completely not possible to be implemented in practice because of the challenge in the rounds of interaction, and hence we started with our work. Now let me, in the last 2-3 minutes, let me give you some idea about how our results look like. So I told you, like, for certain class of problems, we can get complete parallelism, meaning that you do not have to do back and forth to the server. So this one class is like you are doing a single parameter learning. Let's say there is only one parameter, the model has only one parameter. It might be that with the Parkinson's example, it's the gyroscopic movement of the phone, that single number we are using as a parameter for predicting whether the person has Parkinson's disease or not. Now, the first thing we do is we translate this problem to a seemingly natural problem of computing statistics about a data. It's not just training a learning algorithm, it's actually computing statistics about data. So we translate this problem into computing median about a bunch of data samples. And the beauty of this translation is that this translation will not incur additional error than the error of the original algorithm. So this translation is benign in that sense. But once you translate this problem into estimating the median of a bunch of data samples, still under the constraint of local differential privacy, we can use the standard hammers from differential privacy literature to solve the problem. So the main contribution was this translation from the machine learning problem to a problem where you compute median statistic. And this, when we got the result, actually it was completely surprising to us that such relation actually exists. So this is the high-level idea of our first result. The second result, which is multi-parameter learning, where you do have adaptive interaction. And as I told you that it is not possible to design algorithms for the general problem of like multi-parameter learning where you do not have adaptive interaction. So you need adaptivity. And our algorithms work in the following sense. You take a bunch of devices, ask a question, then take another bunch of devices, ask a question, and move forward. Now, finally, you produce the differentially private model. So the key feature of our algorithm is that it improves exponentially in the number of rounds of adaptivity without incurring additional error. As I told you, the previous algorithm, which was the best known before our work, that required, if you are dealing with n samples or n devices, the number of rounds of adaptivity was n. We can do it in log n time. So this is an exponential improvement in the rounds of adaptivity. But at the same time, we still keep the good feature of their algorithm, that is, you still interact with one device only once. So these are the good news, but let me end with a more pessimistic note. Let me give you the bad news. So our load bounds show that if you try to achieve minimal error under local differential privacy, adaptivity is in some sense necessary. And let me try to give you in like 1 minute how the lower bound looks like. And I think in the paper, according to me, this is the most interesting part or the most intuitive part of the paper. So suppose this circle represents the space of all models you want to learn, right? So your true model lies in this space. Let's call that theta star. And it is lying in a small region, basically the small green region around this theta star are the space of good models. Basically means that if you don't get theta star, you don't worry, but as long as you hit somewhere around this theta star, you are good. Now, when you run learning algorithms or machine learning algorithms, you basically probe at different models and get some information about that model, in the sense like how good is that model on your data. Same, this is true for gradient descent or any other optimization method. So what do? You basically can think like you throw a dart at this space, you pick a model, get some information about the data. But notice that we want to show that there is need for some round of adaptivity. So right now we are saying, like, suppose there is no adaptivity, then what happens? So you throw a dart, you get some information. You throw another dart, which has to be thrown independently of the previous dart, and you get another information about that model. Now, since the space of these models is high dimensional, but just by throwing darts at this space, it is very unlikely that you will actually hit that green region. This shows that completely non-interactive algorithms will not let you get closer to the true model. However, if you look at the information about one of these darts, like if you look at what this dart is saying, then that immediately will point to the ball where the true model lies. Basically, this shows that with one round of adaptivity, you can actually find out a good model. Now, this architecture can be recursed again and again to get basically higher rounds of adaptivity. So now to end, so our next steps, we want to implement these algorithms. Right now it's the theoretical work and evaluate empirically. We want to interact with industry and try to possibly deploy them in practice. Our current lower bounds are not tight. We hope the lower bounds are tighter. So either we want to improve the lower bounds or we improve our algorithms. I think the former is more plausible. Finally, to conclude, I told you about new protocols that are almost fully parallel, and the accuracy, either the accuracy or the degree of parallelism goes down as you increase the number of dimensions in the problem. We showed some impossibility results that adaptivity or adaptive interaction is somehow ingrained into the problem. Finally, if you haven't heard my talk in the last 20 minutes, if you remember this slide, that itself is worth it. And that's what my talk is about.
And any questions? Go ahead.
Hi, Sahar Maslum from George Mason again. My question is more related to differential privacy. I would like to know what parameters did you use for differential privacy? For example, what was the epsilon or delta if they use the epsilon delta differential privacy?
So this is first of all a pure epsilon differentially private algorithm, everything which I've told about. And the second thing is we did not use the parameter because it was a theory work, so we use epsilon as it is. Yeah, so
Just general, because you had the experience to being in Apple, and I heard that Apple is kind of in their summits, actually, they talked about they have differential privacy in order of aggregating data from user devices. So what is the practical values for these security parameters?
I do not think Apple has released that parameter publicly, so I can't tell the number. But I guess like most companies are using in the scale of 1, at least in the distributed setting, 1 or like aroundish 1. Epsilon has to be 1.
Thank you. So thank the speaker again.